So what we're going to do is we're going to take the stuff that we've already done, which are separable differential equations, and we're going to marriage that with something you learned last year called the Pert equation. Now when I asked you the other class, many of you didn't remember the Pert equation, but it'll come back to you as we work our way through the slideshow. Okay? So, once again, the clicker has to be turned on. So we're going to talk about population growth. Population growth is just one of the examples that we're going to talk about. In essence, we're going to look at exponential growth models and exponential decay models. Do those terms sound familiar to you? The spread of disease follows an exponential growth model. I get sick, I make 2 people sick, they make 2 people sick, etc., etc. Okay? Brooke turns into a zombie. She bites 2 people. Those 2 people bite 2 people, and next thing you know, we have the Walking Dead. Okay? So a lot of things in the real world follow an exponential growth or decay model, and we're going to do the math associated with those.
This pie is really good.
Which pie?
The pie that's in your office.
Oh, that's not. You want a little pie? You
A
should
little
eat
pie.
more. You're skinny. You want a blueberry pie?
Wait, they've got more pie.
Is his mom with him? Who is he talking about?
There's more people with you.
Oh, bring him in. I got plenty of pie.
Right.
Okay. What is this? Individual?
You want a blueberry pie?
I mean, I don't say no to a blueberry pie.
Do you want me to split one with them or
No. I got extras.
Thank you.
The band kids chose not to come today.
I told them we should take the scenic route back to the office, and this is why. All right, well, thank
Great.
you.
No
Here,
problem.
hold on.
Can you imagine when they're watching the video tonight? Like, what the hell just happened? Okay, so you should be able to understand the Pert equation. We'll break that down for you. The difference between what you did last year, which you don't remember, and what you do this year is I'm going to show you where that equation came from. Last year, you were just given the Pert equation and you just started plugging into it like crazy. Today, we're going to do some calculus to explain where that equation comes from. Most of the time, you won't have to do what we're going to do today, but occasionally you will be asked to take it from start to finish. All of that will make more sense once we get into this. Like I said, we're going to use the calculus to... Okay, and you should be able to believe in yourself, because I believe in you. I don't know. You know. Feeling sentimental when I was writing this. Let's move on, because it's awkward for everybody. Pert equation. There's the Pert equation. A stands for the final amount. P stands for the starting amount. Okay. So Brooke turning into a zombie, the starting amount would be Brooke is 1 person, she would be 1, and then by the end of the show we have millions of people that are turned into zombies. You'll also see that little O in the corner. That's frequently called P naught, because it's the initial value. Sometimes you'll see the Pert equation written as P equals P naught e to the RT power. Okay, so I'm going to stay with that P naught expression so that you get comfortable with it, depending on how it's written. R is the growth or decay rate. Okay, we're going to look at both ones. Okay, growth, spread of zombies, spread of disease, growth of investments. Decay, the decay of radioactivity, for instance. You've seen Oppenheimer, that kind of fun stuff. And T, of course, is time. Okay? So last year, I know you did the Pert equation and you plugged in chug. However, in calculus, we will sometimes rewrite that Pert equation. You see at the bottom, we'll do C e to the kt power, where C is your starting amount, your starting constant, K is your growth or decay rate, and then T again is also time. And then we'll talk a little bit more about dy dt in a second. Does any of this look familiar? A little bit? Okay, good. All right, now we're just going to dive into it. Okay? So we're going to take this example. We're going to work with some bacteria here. And I'll let you read that problem. That's on your slideshow, right? Okay, good. So I don't have to wait for you to write the whole thing out. We're going to do the first one from start to finish, meaning we're going to do the calculus in order to solve this problem. And then some of the other examples that we'll do later on, we'll just dive right into the Pert equation. Sometimes on the AP test, they will expect you to derive it. Sometimes you can just plug and chug. Okay? And the breakdown usually comes about as whether or not this is a free response question or if it's multiple choice. If it's multiple choice, you can just do your thing and come up with the answer, A through E. If it's free response, you're obviously going to have to show your work. Okay, so the key here is this sentence. Assuming that the rate of increase is directly proportional to the number of bacteria present. Okay, we're going to start with that. There's a couple crucial words in that sentence that we need. The first one is the rate. When you hear the word rate, what does that bring to mind?
Change.
Rate of change, which is also?
Slow.
Which is also, correct, which is also? I heard somebody say it. Say it loud, say it proud. Thank you, it's a derivative. Okay, so now we got to get our terminology correct. What do we want to use to represent the number of bacteria? What letter?
B.
B is a good call. Okay. So the rate of increase of the bacteria, dB dt, is directly proportional to the number of bacteria present. So you'll recall, today's Thursday, right? Yeah. Tuesday, we had that one problem that we went over where I had the K in there, and I talked about this idea of a proportionality constant. Now it comes into play. We get KB. Okay? So now seeing that equation and rereading the sentence, that should make some sense to you. Assuming that the rate of increase, also known as the rate of change, of the bacteria is directly proportional to the number of bacteria present, where B is the number of bacteria. Any problems so far? No? Good. Okay, so now we're done with the example for a second. Now we're going to do some calculus. This is a separable differential equation, so we have to do just that. I should have, I made a mistake here. I'm going to need more room. So I'm going to come in here and get rid of this. I'm going to go back here, and I'm going to go dB dt is equal to KB. And now I start solving the separable differential equation. What's the most important thing about a separable differential equation? Separating the differentials, correct. So I'm going to leave the K on this side. Why? Because that's just the norm. You don't have to, but that's what we normally do. So I get 1 over B dB is equal to K dt. Next step. Integrate. Abby, what's the integral of 1 over B dB? Donkey Badger.
I don't remember. I know, that's why I put it.
Via.
Plus
No plus C. We'll save that for the other side. Okay? Leona, what's the integral of K dt?
1/2 K.
Oh, got you. I knew I could sucker you in.
Oh, is it immediate times K is the constant?
K is a constant, so what would the integral be?
K
KT. Very good. Okay, so remember when we started separable differentials, we said, hey, we're going to have a bunch of C's flying all over the place. Let's just leave the C with the X's. The same is true with these. We're going to try to leave the C's on just one side, and the norm is to leave it with the T, not the other stuff. Pregunta?
Can it be the absolute value of B?
Yes. Technically speaking, we should do this. Okay? Now, let me ask you a question, Via. Why didn't I put the absolute value on there? A, because I forgot. B, because I didn't care and I have a bad attitude. Or C, I knew something secret that you may not have considered before you asked that question. Or D, all of the above.
Abby said that it was an actual log of B, so I said it to you so that because she wasn't gonna say
A, B, C, or D?
D.
C, correct. Why did I not include an absolute value, Mr. Kurtz?
You can't have negative bacteria.
Yeah, you can't have negative bacteria. So yes, from a mathematical standpoint, you're 100% correct. The absolute or the integral of 1 over b should be the natural log, but because we're talking about a positive number, it makes no sense to say, how many pets do you have? I have -3 pets. That doesn't mean anything, okay?
So should you write like ln natural log v and then just remove the natural log in like the layer after?
I wouldn't even write it, yeah. But now that it's there, we'll deal with it in a second. Okay. Any problems so far? Excellent. So now, they give us a little bit of information here. They give us this. Okay. Can I use, okay, so what's the problem? I don't know what my starting amount of B is. I don't know, there's a lot of things I don't know. But let's keep going mathematically before we come to the problem. Here, I would like to get B by itself, so what do I do next? Kush. Yeah, you do the E trick. Okay. And this, you'll remember Tuesdays where I talked about that thing that's going to keep popping up. Okay, bring this up here. E to the natural log of anything is its anything. That's B. That makes me happy because now I know the number of bacteria at any point in time. E to the KT plus C is the same thing as E to the C times E to the KT. And now you see where things are starting to look familiar. What's E to the C? C, right. So that this becomes this. That's a C, by the way. And now, actually, let me clean that up because that's very confusing and it bothers me. This and turn this into a C. And now you see, I didn't mean that, but now you see that we have something in the form of a Pert equation. But I've got 4 variables in that problem. So I need to find a couple things. All right, so number 1, I know from reading the problem that my K value, the growth rate, should be just that. It's a growth rate, not a decay rate. The number of bacteria are getting larger. They're reproducing. Okay? And I know that also because it says we go from 600 to 1800 in 2 hours. How can I use 600 to 1800 in 2 hours to clean that up and to solve for some of the other variables? Hey.
Because you have a B value, a C value, and a T value, so you can solve for K.
Okay, so what's my B value?
1800.
Interesting. What's my C value?
600.
Beautiful. And my T value?
2.
Well done. Okay, do that please. Solve for K. And store the number once you solve it. I'm going to get my calculator to play along with the kids at home. Okay, so did we get K to be 0.5493061111443?
Yes.
Yeah, okay. I can't stress this enough. I know the College Board says you need to round to 3 decimal places. When you're doing these types of problems, you must store the number. If you chop this off at 0.549, it's going to affect the final answer. So we want to store that somewhere. You have a bunch of places to store it. You have 26 places to store it. You want to store it in X? Great. You want to store it in K? Fantastic. Doesn't matter. For the sake of continuing to solve the problem, though, by the way, is everybody good solving this? I assume that we're all okay, but divide both sides by 600, take the natural log of both sides, divide by 2, right? Okay. K is equal to 0.549. Before I go any further, I'm going to ask myself a simple question: does that make sense? And the answer is yes. It's a growth. The number of bacteria is increasing, so I should get a positive K value. Which means, for part A, I have B is equal to 600 times e to the 0.549t. Okay? That's the formula. There's only 2 questions I can ask you from this point on. One of them is part B. After a certain amount of time, how much bacteria do I have? The other question would be, how long does it take to get this many bacteria? Okay. So for this one, I asked you 4 hours. At the end of 4 hours, how much bacteria is there? So please do that calculation. Anyone?
Got 5,400.
I also got 5,400. Bacteria. Right? Did I spell that right? Bacteria. Yeah. 5,400. Okay, so this is an argument that comes up. If you did your calculations correctly, your calculator should have spit out exactly 5,400. Yes? What happens if I get 5,400.021? What do you do? So logic would dictate you can't really have a fractional part of a bacteria. You can't have a fractional part of a deer. You can't have a fractional part of a neighbor, etc., so that you would chop off at the whole number. What the College Board does is they assume that you stay accurate to 3 decimal places until it specifically tells you in the problem. So a lot of times, I can think of one problem in particular where it has to do with the number of deer on an island. And they say in the problem, to the nearest deer, how many blah, 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 blah. If they don't say that, then give the decimal value. Even though the decimal value doesn't make any sense. If you're calculating the number of people in Arlington Heights and you get 0.75, you're not going to have 3/4 of a person. It's messy. Okay.
What about if you're on your bike going into school and you get hit by a bus? And you become 3/4.
Of a person.
Yeah.
Well, that's a happy thought. But you still be a whole person. Just missing your legs, is that what you're saying?
Like a deer. Yeah. Like what if the deer
You end up looking like a deer from getting hit by a bus? How does that happen? You like the grill becomes antlers? And you forage in your backyard for food every day? Okay.
I was imagining a deer is like, well, that's how I feel every time I get hit by a car. You know? It's just,
I got this.
Just my thing.
Let's move on. Okay. Radium. Who's an AP Chem? Kush. Jessica. Kush. Can you explain what Half-Life is to, other than an amazing video game that was a pioneer in the realm of first-person shooters, but we're going to ignore that and talk about Half-Life for radiation. What is Half-Life?
So we start with 100, and then half that's like 2 years. So 2 years is gonna be 50, and the other 2 is 25, and the other 2 is like.
Yeah. Did you all know that? So that's how radiation works. Like, do you all know what Chernobyl is? Does anybody not know what Chernobyl is? Okay, good. So Chernobyl, when Chernobyl melted down, it released a certain amount of radiation, and it has a certain level of radiation. After so many years, however much radiation is there is decreased by a half. For something like Chernobyl, the number is astronomically high. They're never going to not be radioactive there because it just keeps chopping in half. Some things have a very small half-life. Some things have a very big half-life. Okay? So again, it's the amount of time it takes for half of the stuff you start with to just disappear. For radioactivity, it just goes away. It's magic. Now, on the flip side of that, we have something called a doubling time. It's the exact same thing, but in reverse. How long does it take for something to double? Where would you use doubling time? For your graduation this year, you get $2,000. You put it in a bank account. What's the doubling time on your $2,000 investment? In other words, how long will it take for $2,000 in a bank account to change into $4,000? Okay, this one's a half-life problem. Okay, any questions so far? This requires a different way of thinking. So if you read the problem, we can solve a bunch of stuff from just the first sentence, ignoring parts A and B, which I'll do for a second. One thing I'm missing is the K value for radium. Yes, you could go to the interwebs and look up the decay rate for radium, but we're going to find it on our own. If I go back to a general equation, let's use the Pert equation here. If I do A times P naught E to the RT, what I'm missing is R. What I know is T. I'm assuming you understand that this is T, because it's in years. But I'm also missing the starting amount. Let's forget about part A and B for a second. Let's just start from there. So let's suppose P naught is, as Kush said, 100. What would A be? 50. If I start with 1,000, then A would be 500. If I start with P naught, what would A be? Half of P naught. Okay? What you start with in this calculation is irrelevant, because what's the first thing I'm going to do? How would I solve that? What's the first thing you're going to do? What's the first thing you did here? Didn't you all divide by 600? Okay, so what's the first thing I'm going to do here? I'm going to divide by P naught. What's P naught divided by P naught? 1. Whoops. E to the RT. Okay, so let me stop for a second and make sure you understand that. You can calculate the decay or growth rate without knowing the amount of stuff that you start with if you just know the amount of time, because no matter what you start with, when you do that first step of division, you're always going to end up with a half. If I start with 100 and I end with 50, 50 divided by 100 is 1/2. 1,000 divided, or 500 divided by 1,000, you're always going to get to that. Now there's two variables in that equation, but we know what T is. Okay, so solve for R, please. And when you're done, check to make sure it makes sense. Did you get a negative number because it is a decay? Little help, please. Give me a number.
Negative 4.332170
Okay, so give me 3 decimal places just for writing it up here. 4.3.
32.
Can somebody else? Whoa, that's a 2. Can somebody else confirm?
Yeah.
We're good.
And then E to the negative 4.
E to the negative 4.
Yeah.
Oh,
Well, like,
so that means times 10 to the negative. Oh, that's fun. So what is that actual number? 1, 2, 3, 4. Fill in the gaps with zeros. So R should be negative 0.00043332. What? Well, yeah, it's taking 1,600 years for that radium to decay. So our R value should be very, very small, very close to 0 because very little is happening. Okay? All right, so now we know R, and we still don't know the initial amount until I read problem A. Because problem A says finding the remaining from 500 milligrams of pure radium after T years, which means my equation becomes A is equal to 50 times e to the negative 0.00043332 T. And we're back to that same scenario I had on the last example. Only two questions. How much radium do you have after X number of years? Or how much time does it take to get X number of things? Okay. And then part B is the opposite of what I asked in the last example. How long is it going to take to get 20 milligrams from 50 milligrams? Okay, so before we even do the calculation, let me ask you a logical question. Will the answer to part B be bigger or smaller than 1,600?
Bigger.
Bigger, because 20 milligrams is less than half. Okay, so part B, we get 20 equals 50 times e to the negative 0.00043332 t. Solve that, please, for t, and make sure you get a number bigger than 1,600.
When it comes to the rule of writing for decimal places, I'm like, if you write 0.0004332, is that like?
Think of it as significant digits.
Yeah.
So technically, I think they would expect 0.00433. But we threw the 2 in there just because we're feeling saucy.
How?
2,115 point blah, blah, blah? Units? Years. Whoa. Okay. So it could do with, have to do with the fact that. That's weird. Okay, so you did. In general, you did the natural log of 20 divided by 50, divided by that stored number of 0.00043332.
Yeah.
Anybody else get 2,114?
Oh, no, never mind.
Oh.
Fix itself.
It's magic. Okay, beautiful. Any questions? You'll notice in this problem, I didn't derive the equation. I didn't start with a separable differential equation. I just dove right into the Pert equation. Well, how do you know when to do that? It'll tell you. Use calculus to derive the formula that represents the amount of radium after T years. But it's a lot easier when you just start with the Pert equation. Questions on this bad boy? Okay. I think I got one more? Yeah, one more. Law of cooling?
Yes.
Okay. Newton's law of cooling. It's real simple. And again, for those of you that AP Chem can help me. If I bring a pot of boiling water into this room right now, what's going to happen? Good. What else happens though? Oh, that's your ripcord. You're like, I'm done. I'm out of here.
The air
That's all
heats
I
up.
know.
Good. The room will heat up. However, the change in temperature of the water is a lot more drastic than the change in temperature of the room. Same thing is true with a cup of coffee. If I bring a cup of coffee in here and I set it down on the desk, that coffee, holy smokes, is it Friday yet? That cup of coffee is going to cool down pretty rapidly. The room will also heat up. You just won't notice it because the effects are very minimal. Okay. The law of cooling, as you can see in the explanation, the rate at which an object cools is directly proportional to the difference in temperature between the object and the surrounding medium. So for the cup of coffee example, the cup of coffee would be the object, the surrounding medium would be the temperature in the room. Okay? So we get an equation that looks something like this. Let's change colors. Let's work with blue. The rate at which the object cools, so the temperature, Y is the temperature of the object, is directly proportional to the difference in the temperature between the object and the surrounding medium. So if you read further into the problem, we're dealing with a room that's 75 degrees. That's why I put the 75 in there. And we're going to derive this one from scratch because it requires a little bit more work. Okay? But it also requires a little bit different setup because we're doing a law of cooling problem. If the room is 80 degrees, you change the 75 to 80. Here we go. Separate the differentials. 1 over y minus 75 dy is equal to c dt. Okay, now look at what I did there. I left the y minus 75 together as one unit and just divided. And now this requires a little bit of conversation. Again, remember, just because you see 1 over something and you take the integral of it, it doesn't mean it's just the natural log of that. It's actually supposed to be done as a UDU problem. And now that I've said that, I'm going to end up contradicting myself. Because when I do a UDU problem, it does just turn out to be the natural log of y minus 75. Because the derivative of y minus 75 is 1. What's the antiderivative of c dt? CT, very good. Oh, wait, bad choice. Maybe I shouldn't use C. Let's turn this into a K, because we're going to do a plus C here. Ooh, I got sloppy there. The next step is going to become second nature to you. The E2 trick. Y minus 75 is equal to C times E to the KT. Okay, now what? How do I get rid of some of those variables? Go.
Separate the e to the kt and e to the c, and then it's just going to be e to the kt times c.
No, I already did that. That's my final product. That's my
I
equation.
missed
You
that
didn't see
part.
that? There you go. Yeah. So you're right. I would separate that, but I did already. You just didn't see it.
No, I guess I was keeping up.
Abby?
Can you plug in like the temperatures?
Yeah. Okay, so how do I do that? If an object cools from 125 degrees to 100 degrees in a half hour, when surrounded by air temperature of 75 degrees, find the temperature at the end of the next half hour. What's what? Because I got a Y, I got a C, and I got a T, and I can use those to solve for K. So what's Y?
Is that 100?
Mm-hmm. No, sorry. Oh, yes, it is, because we're starting, it's cooling, sorry, I'm an idiot, yes.
And then C is 125.
Perfect, and T is?
Like 1/2 is
Perfect. Okay, we're working with hours here. So 100 minus 75 equals 125 e to the 1/2 k.
Would it be 125 minus 75?
No. Our starting amount is 125, it's cooling. Our final amount is 100. Okay? Now, do we need to spend the time to solve the problem? Well, what's going to happen? Let's talk about that. You would solve for k. Will that k value be positive or negative? Negative, because it's going down, right? It's a decrease, it's a cooling. So the values are going down, so k would be negative. And then when you plug the k back in there, then you can add, then we get back to that standard equation of here's the time, what's the temperature? Here's the temperature, what's the time?
That concludes our new material lessons for the 23-24 calculus class.
Yeah.
It saddens me.